Welcome back, everybody. Let's continue to talk about the related samples t-test. The last time we were together, we discussed the basic rationale for the test, and we also discussed when it's appropriate to do the related samples t, and that's specifically during a within subjects research design, also known as a related samples research design, where we measure the same people more than once. We discussed the distribution of mean difference scores, and we also talked a little bit about the estimated standard error of the mean difference score. In this video, we'll get some experience computing that and also 95% confidence intervals as we work through the 4-step hypothesis testing procedure with our first related samples t-test. Let's work through our first example. A medical researcher believes that stress increases the symptoms of asthma, so she decides to test if relaxation training might reduce the amount of medication required by asthma sufferers. When we're talking about medication in this example, think about those self-administered inhalers. A sample of 5 patients is selected. Of course, in the real world, we would typically measure many more patients, but when we're doing this by hand, we have to keep the sample size reasonable. During the week before and after treatment, the researcher recorded the number of doses each patient self-administered. Does relaxation training alter the amount of medication needed? Test with an alpha of 0.05 two-tailed. As you can see in this summary paragraph, I don't provide you with any statistics, like the sample mean difference score or the standard deviation of the difference scores or anything else like that. We're going to have to compute that stuff ourselves by hand. So let's change views and get started. Here is our data. It looks like we have data from 2, 4, 5 different people. So let's make note of that. N equals 5. I've already computed the difference scores for each of these 5 people. And you can see every single one of those difference scores is negative. So what that's telling me is that for every single one of these patients, they self-administered fewer doses after the training compared to before the training. So at least for now, it looks like that therapy might be relatively effective. We just need to test if we have a statistically significant difference from time 1 to time 2. In order to do that, we go through the 4-step hypothesis testing procedure, and ultimately we compute a t-statistic. And in order to compute that t-statistic, we need to compute a few other things first. So for example, we need to know the mean difference score, so eventually we'll compute that. And in order to compute standard error, we would need to know the standard deviation of the difference scores. Keep this in mind. In order to compute standard deviation, we need to compute sum of squares. So I've set it up so that we're ready to compute the sum of squares of the difference scores. This formula right here is the same formula that we've always used for sum of squares. Everywhere where there was an x in the equation, just referring to an x value, a typical raw score. In each situation where there was an x, I just put a d because now we're dealing with the difference scores. So let's get started computing this prep work that we're going to need along the 4 steps. Let's start by summing up those difference scores, and then we'll compute a mean difference score. We'll just add up -6 plus -3 plus -5 plus -1, and then finally plus -5. That equals -20. Keep in mind, all of our analyses are based on those difference scores. When we compute n, we ask ourselves, how many difference scores do we have? We have 5 of them. So I'm going to divide by 5 to compute the mean difference score, and that equals -4. I'll write in those values. We have -20 for the sum of d, and our mean difference score was -20 divided by 5, which equals -4. So on average, these patients are giving themselves 4 fewer doses after the relaxation training. Well, as I mentioned, in order to compute the standard error later on, we need to know the standard deviation of those difference scores. And in order to compute the standard deviation, we need to know sum of squares, because sum of squares is the basis for computing variability. When we look at our formula right here for sum of squares, we can see that we're going to need the sum of the squared difference values. So I put a column up here for squared difference scores. We also need to know the sum of the difference scores squared. We already know the sum of the difference scores, so we can easily square that value. So it looks like the next thing that we need to do is square each one of these difference scores. Let's do that next. -6 squared is 36. -3 squared is 9. Then we have 25, 1, and 25. Let's go ahead and add up those values to find the sum of d squared. We have 36 plus 9 plus 25 plus 1 plus 25. That equals 96. 96. Now we have everything that we need to compute sum of squares. The sum of d squared was equal to 96. And now we want to subtract this fraction. The numerator calls for the sum of d, that quantity squared. Here's the sum of d. We need to take -20 and square it. -20 squared is 400. The denominator asks us to divide by n. We know that n equals 5. So in other words, we need to subtract 400 divided by 5. We'll work that out in the next step. We're left with 96 minus 400 divided by 5 equals 80. So it's 96 minus 80. And 96 minus 80, of course, equals 16. So sum of squares equals 16. I think that's all of the prep work that we're going to need. So let's change views and get started on the 4-step hypothesis testing procedure by working on step 1. Of course, in step 1, we state our hypotheses, and we have 2 competing hypotheses. Our null hypothesis always states some form of saying there's no effect. In this case, the most appropriate way to think about it is there's no difference from time 1 to time 2. The alternative hypothesis, of course, will state that there is a difference. So here's an example for how we can write that. The null hypothesis would state that the population mean difference in doses from time 1 to time 2 equals 0. In other words, there's no difference in doses. The relaxation training had no effect on the number of doses the patients self-administered. We're doing a two-tailed test, so our alternative hypothesis needs to state every other possibility. So it states that the population mean difference in doses from time 1 to time 2 is something other than 0. That leaves open the possibility that we might find statistically significant results in either direction. We might find that the relaxation training lowers the number of doses that the people self-administer, but of course, we might find the opposite result. We might find that after relaxation training, the patients self-administer even more doses. But of course, we've already had a look at the data. We know that the sample mean difference score equals -4. So if indeed we do find a statistically significant result, we know it will show that the relaxation training led to fewer doses self-administered. Okay, that was step 1. And we're going to proceed along assuming that the null hypothesis is true. As we move into step 2, now we need to determine how much evidence do we need to reject the null hypothesis. In order to find how much evidence we need to reject the null hypothesis, we're going to have to create a distribution of all possible sample mean difference scores. Let's change views and work on that together. First, let's be clear about what we're looking at. This is a distribution of all sample mean difference scores. And remember, we create it based on the null hypothesis being true. That means on this x-axis, we're plotting sample mean difference scores. And right below it, we'll put t-values. And according to central limit theorem, based on that null hypothesis being true, the population mean difference score should be right in the middle, and it should equal 0. Not all of those sample mean difference scores will equal 0, of course. There will be some natural variability from one sample mean difference score to the next. The standard error of the mean difference score measures that, and we'll compute that value just a little bit later on, but we can label it right now. That's the estimated standard error of the mean difference score. Let's not forget the real reason why we're here. We're here to locate our critical regions, and we're using an alpha of 0.05. So we need to find the t-values that mark off the most extreme 5% of the sample mean difference scores. In order to find those t-values, we first need to compute degrees of freedom. So let's talk about that for just a quick minute. So how do we compute degrees of freedom? I've mentioned to you that the related samples t-test is very similar to the one sample t-test. And you'll recall for the one sample t-test, we simply looked at the number of scores overall and subtracted 1. Well, we're back to a situation that is very much like that one sample t-test, because what we are analyzing are those difference scores, and we just have one group of difference scores. So all that we need to do is take the number of difference scores and subtract 1 to compute degrees of freedom. So we need to ask ourselves, how many difference scores do we have? And we have 5 of them. Remember, we measured 5 people. If we have 5 people that we measured, we're going to have 5 difference scores. The reason why I'm harping on this is because sometimes students get confused and they see the data from time 1 and they see the data from time 2, and somehow in their heads, they see that the sample size in this case equals 10. That is not true. We have data from 5 people. We are no longer analyzing their actual scores. We are simply focusing on their difference scores. How many different scores do we have? 5 of them. So, if n equals 5, degrees of freedom must equal 4. Let's go ahead and look that up. Here is our t-table. We're going to be using a two-tailed test with an alpha of 0.05. We know that we have 4 degrees of freedom. So let's move down this row until we find that column, 0.05 two-tailed. Right there, we see that our critical values will be positive and negative 2.776. Right in the middle, we'd have a t-value of 0. On the right-hand side, we have a critical value of 2.776. And on the left-hand side, we have a critical value of negative 2.776. So now we know how much evidence we need to reject the null hypothesis. What we need to do right now is figure out, where is negative 4 in this distribution? We found that from time 1 to time 2, the patient self-administered 4 fewer doses. Is negative 4 one of these sample means in here that's likely to occur just by chance? Or is negative 4 one of the sample mean difference scores that's unlikely to occur by chance? The only way we can find out where it's located in that distribution is to transform it into a t-value. Let's do that next. That's what step 3 is all about. Here we are at step 3, and here's the t-formula that we need to use. We already know the sample mean difference score. That's negative 4. We know that this value right here always comes from the null hypothesis, and the null hypothesis states that the population mean difference score is 0. So we know that value. What we don't know right now is the estimated standard error of the mean difference score. So let's go through our equations and figure out how we can find that. Here is our formula for standard error. We need to know the standard deviation of the difference scores, which we don't know, and we also need to know the number of scores that we're dealing with, which we do know, that's 5. So let's find a formula for standard deviation. Here is a formula for standard deviation. In order to know standard deviation, we need to know variance, s squared. Let's find a formula for variance. Here's a formula for variance. How do we compute variance? We need to know sum of squares. Do we know that? Yes, we do. Do we know degrees of freedom? Yes, we do. That's how we know this is where we should start. When we did our prep work, we found that sum of squares equals 16. Remember, sum of squares is the basis for variability. We need to know this to compute variance. All that we need to do now is divide by degrees of freedom. We just computed that, and we know it equals 4. 16 divided by 4 equals 4. So the variance for the difference scores equals 4. You should know by now that the standard deviation is simply the square root of the variance. So if we take the square root of 4, we will find that the standard deviation of the difference scores equals 2. Now that we know the standard deviation of the difference scores, we can plug that into our formula for standard error. 2 divided by the square root of 5 will give us 2 divided by 2.24. Let's take 2 and divide that by 2.24. That equals about 0.89. Remember, the standard error represents, on average, how much those sample mean difference scores will differ from 0. Based on the value that we just computed, it looks like those sample mean difference scores will differ from 0 by about 0.89 self-administered doses. In other words, the average error rate is less than 1 dose. Okay, now we have everything that we need to transform our sample mean difference score into a t-value. The sample mean difference score was equal to 4. Remember, this value right here is always based on the null hypothesis, so that's always 0. And then we're going to divide by the standard error. So I'm going to key in -4 and then divide that by 0.89. And that equals -4.49. Let's go back to step 2 and plot that value. Our sample mean difference score of -4 transformed into a t-value of -4.49. Right here is a t-value of 0. Right here is a t-value of -2.776. -4.49 is clearly more extreme than that. We're clearly to the left of that. In other words, we are inside this critical region. So let's mark it off. Right about here would be -4.49. And that's where we would find our mean difference score of -4. So clearly we are inside that critical region. And that's the main thing we need to know, if we are inside the critical region or if we are not. When we conclude that yes, we are inside the critical region, then we know the 3 follow-up questions that we ask ourselves will all be answered yes as well. Here's the first follow-up question. Should we reject the null hypothesis? Yes, we should. We should reject the null hypothesis, so go ahead and cross it out, and then check off the alternative, because now we embrace the alternative hypothesis. The alternative hypothesis states that the population mean difference in doses from time 1 to time 2 is not 0. And we have evidence to say that it's less than 0. In fact, our best guess is that people give themselves 4 fewer doses after the relaxation training. Second follow-up question, do we have statistically significant results? Yes, we do. The average difference that we found, 4 fewer doses, is very unlikely to be found just by chance if the null hypothesis is true. So in other words, it makes us question the null hypothesis. Our data is inconsistent with the null hypothesis. That's why we rejected the null hypothesis. We do indeed have statistically significant results. Follow-up question number 3 asks, is it possible that we're making a type 1 error? Yes, it is possible. Remember, anytime we reject the null hypothesis, there's at least some possibility of making a type 1 error. What is the probability of making a type 1 error? Well, in this situation, we used an alpha of 0.05. So over the long run, in this situation, we will make type 1 errors about 5% of the time. Let's go ahead and write up our results at step 4. Remember, there are 4 things that we need to do. We need to mention if we're going to reject or fail to reject the null hypothesis. We need to interpret our results in everyday language. We need to show how that statistical test would appear in a journal article, and we need to compute the most appropriate measurement of effect size, which in this case will be a flavor of Cohen's d. We mentioned that we're going to reject the null hypothesis. Here's a way that we can write that up a little bit more formally. We found that our sample mean difference score, which was equal to -4, was within the critical region. This mean difference is unlikely if the null hypothesis is true, and that's why we rejected the null hypothesis. In everyday language, what did we find? Relaxation training reduces the number of doses of medication needed by the asthma patients. Now we need to show how this would appear in a journal article. This is a t-test just like any other t-test, so we'll write it up in the same way that we've done in the past. In order to report this result in a journal article, we need to determine if the probability of finding our results just by chance is less than 5%, or if that probability is greater than 5%. And let me remind you, area equals probability. Our sample mean difference value of -4 was located in this small area, so it should be associated with a small probability. Of these 2 options, which is associated with a small probability? That would be p less than 0.05. So this is how we would write it up. We did a t-test with 4 degrees of freedom. the t-value that we computed was equal to negative 4.49. The probability of finding that result just due to sampling error is less than 5% based on a two-tailed test. Now let's compute the effect size. Cohen's d will convert the difference that we see, a difference of 4 fewer doses, into standard deviation units. We will take that value, 4, and then divide by the standard deviation. Remember, we computed the standard deviation right here. It equals 2. Negative 4 divided by 2 equals negative 2. From time 1 to time 2, the patients gave themselves 4 fewer doses. That's equivalent to a reduction of 2 standard deviations. It's that large effect size that allowed us to find statistically significant results with such a small sample size. Okay, we just found evidence that this relaxation training works in that it lowers the number of doses that people give themselves. But remember, we just collected data from this one sample. So the true population mean difference in doses is unlikely to equal exactly 4 because we know sampling error exists. In step 5, let's create a 95% confidence interval around that sample mean of negative 4. That 95% confidence interval will have a very high probability of including the true mean difference score. In order to estimate the true population mean difference in doses, we'll start with that sample mean of negative 4. And then to that, we will add and subtract that critical t-value multiplied by the standard error. So to compute the upper limit of the confidence interval, we'll take negative 4, and then we will add 2.776 multiplied by the standard error of 0.89, and that gives us negative 1.53 doses. In order to compute the lower limit of that confidence interval, again we'll start with that sample mean, negative 4. And now we will subtract 2.776, which is the critical value, multiplied by the standard error, 0.89. That results in 6.47 fewer doses. Let's interpret those results at step 6. Remember, there are 3 important things that we want to cover. First of all, we need to say something about the probability. We also want to say something about what specifically the confidence interval measures. And what we're trying to find within that confidence interval is the true population mean difference in doses from time 1 to time 2. And then, of course, the third thing that we need to include in our interpretation are the values that make up the lower and the upper limits of that range. So here's a good example. The probability is 0.95. Or in other words, we can be 95% confident that the population mean difference in doses from time 1 to time 2 is somewhere between 6.47 fewer doses and 1.53 fewer doses. Remember, this is a good long-term strategy. Over the long run, when we're computing these confidence intervals, 95% of those intervals will include the true population mean value. But about 5% of the time, we will compute a confidence interval that does not include that true value. And that corresponds to our alpha level of 0.05. All right, my friends, that was a lot of work. I think we've done enough for now. In the next video, I'll show you another example, and then we'll also talk about the assumptions that need to be met for the t-test to be valid. I'll see you in that next video. In the meantime, be safe.